Okay, lecture 5 for discrete structures. We're going to talk about relations and functions here. Okay, I want to remind you of something that you learned in one of the last couple of lectures, which is called Cartesian products. Okay, this is just a reminder here. If A and B are sets, then A cross B, which is called the Cartesian product of A and B, equals the set of all ordered pairs x comma y such that x is an element of A and y is an element of B. Okay, let's just practice that really quickly here. Whoops, that's really thick. So let's say A equals the set containing the letters A and B equals the set containing the letters, well, let's do, how about we'll do numbers, okay? 1, 2, and 3. Then A cross B would be the set containing, there will be 6 elements here. One is the ordered pair A1, another one is A2, and another one's A3, and then we'll have B1, B2, B3. Okay, so that's something from a previous lecture. Okay, now I'm going to give you a new definition. This is called a relation. A relation, which we will abbreviate with the letter R, capital R, okay, from A to B is any subset of A cross B. Okay? And then I'm going to add just some more information here. If the ordered pair XY is in that subset, okay, then we say X is related to Y. And then I'll put in parentheses by the relation R, but that's usually implied. Okay? And we often write X, R, Y to stand for X is related to Y. Okay? A little bit more information. A would be called the domain of R. And B would be called the codomain of R. Okay? So let's just look back at the example of A and B that we put up here. Okay, and there I have the Cartesian product of A and B. It's the set consisting of those 6 ordered pairs. So I could take any subset of that I wish. Okay, so let's just take this subset of A cross B. How about we'll include the ordered pair A2 and the ordered pair B1 and the ordered pair B3. Let's call that R. You agree that that is a subset of A cross B, right? Okay, so then R is called a relation from A to B. And we would say A is related to 2, and also B is related to 1, and B is related to 3. Okay? Here's another example that I think might be a little bit more straightforward, because this will just be numbers. Okay, let's do a new example here. I'll just erase that old example. Let's do a new one here. Let's say that A is the set of 1, 2, and 3. And let's say B is the set 2, 3, 4. Okay, let's write down their Cartesian product. It's going to be a lot here. There will be 9. No, more than that. Yeah, that's right, 9 elements here. Okay, we have 1, 2, 1, 3, 1, 4, 2, 2, 2, 3, 2, 4, 3, 2, 3, 3, and 3, 4. Okay? Now, I'm going to put a certain relation on here, and I'm going to explain that relation. I'm going to write this. I'm going to write xy is in this relation if and only if x is less than y. So what would the relation be? Make that a little bigger. I don't want to be too small. So that relation would have these elements. Because 1 is less than 2, then 1, 2 is going to be in there. Since 1's less than 3, then 1, 3 will be there. And since 1's less than 4, then 1, 4 will be in there. 2's not less than 2, so 2, 2 won't be in there, but 2, 3 will. And 2, 4. Three, 2 and 3, 3 won't be there, because 3's not less than 2 and 3's not less than 3. But 3, 4 will be there. So there's our relation. Okay? And we can say 1 is related to 2. 1 is also related to 3. 1 is also related to 4. and 2 is related to 3, and 2 is also related to 4, and 3 is related to 4. So notice 2 is related to 3, but 3 is not related to 2. Okay? Or in this particular case, because I described a particular rule for the relation, and that rule has a special symbol, I could write this way. I could write, instead of 1R2, I could write 1 and then less than 2. 1 is less than 3. 1 is less than 4. 2 is less than 3. 2 is less than 4. 3 is less than 4. You see? Okay, that's what a relation is. Let's do something visual here. You can represent a relation with arrow diagrams. Okay, and let me show you how to do it. This is usually much more straightforward. We're going to take that same relation that we just did, and I'm going to represent it with what we call an arrow diagram. Okay, here's what you do. You draw sort of a bubble here for the set A, which is the domain So what does A have in it? 1, 2, and 3. And then we'll draw a bubble for the set B. And that has 2, 3, and 4, I believe. Okay, and then you draw arrows from the elements of A to the elements in B that they are related to. 1 is related to all 3 numbers in B, right? 1's related to 2, and it's related to 3, and it's related to 4. So I would draw an arrow from 1 to 2. Whoops. Draw an arrow from 1 to 2, and an arrow from 1 to 3, and an arrow from 1 to 4. 2 is only related to 3 and 4, so I would draw an arrow from 2 to 3 and from 2 to 4. And 3 is only related to 4, so I would draw an arrow from 3 to 4. The arrows don't have to be straight. If you need to curve them around each other, that's okay. All right? And then you represent that this is the relation called R, because you can use other letters. You don't have to use R. So what you do is you draw an arrow like this, and you write R. Okay? That's a very simple visual representation of the relation. Now, one kind of relation is called a function. Okay, let me define this for you. A function usually people will use the letter F instead of R if they have a function. Okay, from A to B. Is a relation with domain A and codomain B that satisfies the following two conditions. number 1. For every x in A, there is a y in B such that xy is in F. Okay, so in other words, everything in A is being used by the function. There's nothing in A being left out. Okay, and number 2, if xy is in F and xz is also in F, then y equals z. In other words, everything in A can only have one arrow coming from it. Look at the relation that's still shown at the top of the screen right now. That relation is not a function because 1 is related to 2, 3, and 4. You see? Which means 1, 2 is in that relation, and 1, 3 is in that relation, and 1, 4 is in that relation. But 2, 3, and 4 don't equal each other. Okay, so that relation's not a function. Okay? Now, a little bit about functions here. If x is related to y by a function, then of course we could write x f y. But that's not the way people usually do it. As you know from any math class you've taken in the past, if xy is part of the function, then it's normal for people to write f parentheses x equals y. Okay? So let's look at a couple of examples here. Okay? So I'm going to write down 2 relations. Okay, one I'm going to call C and one I'm going to call L. And they're both relations from the real numbers to the real numbers. Okay? And for the first one, for C, I'm going to write this. For all x, y in the Cartesian product of R, the real numbers, with itself, xy is part of C if and only if x squared plus y squared equals 1. Can you tell why I called that relation C? Because this equation right here is the equation of a circle centered at the origin with a radius of 1. Okay, now I'm going to write down a second relation here, and I'm going to call this one L. For all x and y in R cross R, xy is part of this relation L if and only if y equals x minus 1. Can you tell why I called that relation L? Because that's the equation of a line. Okay? Now, Let's look at both of those. And let's decide if they're functions or not. So for the first one, for C, I am going to draw a bubble here to represent the real numbers, but obviously I'm not going to write all the real numbers in there, okay? It won't fit. But nonetheless, I'll end up writing some of them. And the relation is, I'm just going to write the equation that I'm using for this relation. I'm just going to write x squared plus y squared equals 1. Okay, that's the relation C. Okay, now I claim that C is not a function for two reasons. Look, there's two things that a function has to do, labeled up there in black, 1 and 2. And I'm going to show you that this relation fails both of those. Okay, so number 1, not every number in the real numbers is going to belong in this relation. For instance, let's take the number 2. It's not going to have an arrow pointing to anything because it's impossible for 2 squared plus something squared to equal 1. If the y has to be a real number, then that's impossible. Because if that's true, then 4 plus y squared would equal 1. And so y squared would have to equal -3. And you know that's impossible for the real numbers. To square something and get a negative, you know that's impossible. So 2 is kind of left stranded by this relation. And so that's one reason why the relation's not a function. But this relation fails the other part of the definition for a function as well, which is that, well, here, let me just give you an example. If I put here 1/2, let's say, so what should that be related to? Well, let's just figure it out. 1/2 squared plus y squared needs to equal 1 then, so that means 1/4 plus y squared would be 1, which means y squared would be 3/4. So what would y be? Plus or minus √3/2. So you have over here √3/2, and you also have minus √3/2. And 1/2 is related to both of those by this relation. So that's another reason why this is not a function. Okay, so the first one, C, is a relation, but it's not a function. Okay, now let's look at the second one, L. So you've got the real numbers here. And the real numbers here. And they are related by y equals x minus 1. So I want to point out two things. Number one, no matter what real number I write here, that is going to be related to a number, right? 4 will be related to what? Y equals 4 minus 1, so it'd be related to 3. -1/2 would be related to -3/2. The square root of 5 would be related to the square root of 5 minus 1. So I'm not going to write in any more real numbers, but no matter what real number I would write in there, it's going to have an arrow going to another real number, and only one arrow. Okay? And so that relation L is a function. Now, some functions are defined by formulas and some aren't. This one here is, we wrote y equals x minus 1. So you could in fact write, once you're convinced that it's a function, you can write f of x equals x minus 1. Okay? Since there's a formula. Not every function has to have a formula. Most of the ones that we use do, but it's not necessary. I do want to point out, though, that the name of that function, oh, I'm sorry, it's not f, is it? It's a capital L is what I named that function. I do want to point out that the name of the function is not L of x. The name of the function is L. L of x is the output that you get when you put in an x. In fact, people find it very helpful, at least at first when they're learning about functions. You guys probably have outgrown this, but people find it very helpful to think of a function as a machine where x would go in and f of x would come out. And the name of that machine would not be f of x. F of x is the thing that comes out of the machine. The name of the machine would just be f. And if there's a formula for that function, then you might see that formula written on the side of the function. Okay? In the book, they give 3 quick examples. I'll just go ahead and go over them with you because they're all good. So you have one called the squaring function. Where, let's call it f. Let's call it f. F of x would be x squared. Okay? That's the function f. That's the squaring function. So if you put in an x, you get out an x squared. Okay? There's what's called the successor function. I'll call this one g, because that's the way it is in the book. Now for the squaring function, what's the domain? The domain is all real numbers. Okay? For the successor function, you could have the domain be all real numbers, but that's not the way the successor function is usually used. The domain would be natural numbers. Okay, or if you want to go even bigger, integers. So that means whole numbers. Okay, so the squaring function goes from r to r. The successor function goes from the integers, we do that with a capital Z, to the integers. Okay, I'll call it g because that's the way it is in the book. And the formula for that is g of n equals what's called the successor of n, which just means the next integer. That's just n plus 1. So you put in a number, n, and you get out the next number. Okay? And then let's do a constant function. That's where you always get out the same number no matter what you put in. So we'll call this one h, and that would be from the real numbers to the real numbers, where I'm going to use the variable r here. H of r equals the same thing all the time. In the book they use it too. So no matter what number you put in, you get a 2 out. Okay? And that brings us to the end of chapter 1. You already have an assignment online to be working on. No, you don't. I'm going to put it up today. Sorry. My bad. I'm going to put an assignment up today. So hopefully by the time you're watching this, you have one. And we have nothing on Monday. It's Labor Day. So we won't have another lecture again until next Wednesday. Okay? Enjoy your long weekend.